Um, so we'll get started. I've come to terms with a so last time I was all befuddled because I couldn't figure out. I was searching all here. How do you turn that projector on? And it's like, see, where I was, they had the projectors turned on through like a console that's built into the lecture, and all the classrooms are set up this way, so it's conditioned me to expect there to be a button up here somewhere. There is in plain sight a remote control sitting on the top of this. All you have to do is that, and then we could have seen it. So now I know. So with that, I'll just take a second here to look at the planner with you, hopefully. I wanted to test out if we could actually see things up here or not. Can you guys see that? Probably better if I turn off the light for a second, right? So I still have not provided you homework. I know you all have been emailing me day and night. Where's our homework? Where's our homework? But I will soon get it for you. And I also intend to give you like recommended homework. I'm getting closer to it. But so like today, I'm hoping to cover up through section 1.4. And when I say cover, I mean review. These are things you should have seen a little bit in previous math classes. Like I'm going to try to cover them here, but as best as I can. But you might have to ask more questions afterwards if it doesn't make sense. It's fine. And then Friday, it's supposed to be equations and complex numbers. I think I'm going to need to make a video and post it for you guys. I have to leave town Friday. I won't be here. My father's dying, and I need to be up there. I'm not sure. You know how it is. You don't know when he's going to go exactly, but my mom's brought him home from the nursing home. She hadn't been able to see him for 5 months, because of the COVID. But so she felt like it was time to bring him home. So, yeah, it's, he had a stroke when my now 9-year-old was born, and his health's been kind of declining for a long time. So I think he's at peace with where he is now, but still it's hard, right? So I probably won't be here Friday, just to warn you ahead of time. But I will hopefully post a video, and I'll let you know about that. So, if I have my act together, I'll say everything I need to say tomorrow in the Thursday section, and you can just watch that video, most likely. What's that? Yeah, so no in-person class Friday. But hopefully I'll have your homework published for you by then, so you can start experiencing the joy of homework. Yes. All right, any questions? Okay, so I'll put that away. All right. So I started talking about, I think I've showed you the intervals of real numbers, right? So isn't that right? We looked at closed intervals, open intervals, the open array, and all that. So that's actually in your section 1.1, right? Let's see here. Talk a little bit more about other number systems. That we like to use. Sometimes I'll talk about the natural numbers. Natural numbers for us start at 1, 2, 3, 4, and so forth and so on. These are the natural numbers. There's also something called the integers, right? Integers, they've got 0, plus or minus 1, plus or minus 2, da-da-da. You could also denote this like dot, minus 2, minus 1, 0, 1, 2. So these are integers. Sometimes these are also known as natural numbers. Sometimes they're called the positive integers. That's a good term for them. All right. In addition, we have sometimes the need to talk about rational numbers. What's a rational number? So a rational number is a number that's formed by a fraction of what? So here's a question for you. A circle has a circumference and a diameter, right? All the way around, like the perimeter of the circle, and the diameter is, how much it takes to get from one side to the other, directly opposed. You know that pi is the ratio of the circumference to the diameter, right? So pi is a fraction. Does that mean that pi is a rational number? It does not. Why not? It's what? It's never ending. That's actually that's a good way to look at it. In terms of the decimal expansion, it's never ending. Doesn't repeat. That's right. So rational numbers are formed by p over q, such that p and q are integers, and q is non-zero. Right? These are rational numbers. Now you're right. Fun fact about rational numbers is that these have repeating decimal expansions, right? Now it could be that they just repeat it. It could be that just repeat 0 forever, right? Like 1/4 is 0.25000000. So I mean they can not repeat at the start, but at some point or another they have to start repeating past some point, right? But in contrast, pi, right, which is the ratio of the circumference to the diameter, right? It is a ratio of two numbers, but it's what? It's 3.14159137810, so forth, right? It never, yes?
Is that P over Q? Or?
Yeah, P over Q. Oh, I'm sorry. Is it not big enough? Or is just my Q is funny? My Q has always got this, my Q has arms, whereas P is, I don't know what it is in terms of stick figure terminology, but it's P. Yeah, well. So yeah, what that means is that you can't construct a circle, apparently, that has a circumference and a diameter, which are both whole numbers. Which is kind of shocking, right? Seems like, why shouldn't that be possible? But we've proved it. We've proved that with math, actually. Because we have proved that pi is actually an irrational number. By the way, this is a lie. I just make it up after this point, because no one knows the expansion of pi past about that. So you can just make up numbers. Every so often I meet a student who's memorized 10 digits, but they're pretty rare. So if you lie about mathematics, lie with confidence. People will believe you. It's a general life lesson, right? I shouldn't teach you to be salespeople. You should be honest. Anyway, sorry, I had a bad experience with an unlimited plan on my cell phone yesterday. I spent an hour on chat yelling at them. Unlimited and 30 gigabytes are not the same. If it's a 30 gigabyte plan, call it a 30 gigabyte plan. Don't say unlimited. Does this seem fair? Yeah. So, because my wife was planning to work, and then all of a sudden, I think it had something to do with my children refreshing their copy of Fortnite or something, which apparently takes several gigabytes. Anyway, sorry, back to the math. So natural numbers, integers, rational numbers, right? Great. We will run into these things. What are irrational numbers? I don't have a symbol I usually use for it, but if we take the real numbers and take away the rational numbers, this is called set difference. So this would be x in the real numbers such that x is not an element of q. These are the so-called irrational numbers. There's lots and lots of these, but we really only know the names of a few of them, like pi. Later we'll talk about e, the exponential, right? But there's as many of, I mean, there's more of these actually than rational numbers in some sense. The rational numbers actually are as big as the integers or the natural numbers. You can build a bijection, a one-to-one correspondence between rational numbers and these guys. Whereas the irrational numbers, they're like as big as the real numbers themselves. There's lots more of them. I shut up. That's not this course. All right, so the other thing that we need beyond intervals, because sometimes I'll ask you to, to give the answer to a problem in terms of interval notation, but you need more than just the 10 intervals I showed you before. You need union in order to make sense of things. So an example that I shared last time with the other class, which I think is good, is describe, say, x, absolute value of x greater than 1. Right? Find the solution set to this inequality. I'm sorry, am I writing behind the thing for you? So this is find the solution set. So how would you think about finding the solution set to the absolute value of x greater than 1? There's an algebraic way, there's a graphical way. Which way would you like to see, the algebraic way or the graphical way? I heard algebraic, I heard graphical. I guess I have to do both. So algebraic, if we have, curses. I'm going to do graphical. The algebraic's kind of messy here in some sense. So here's the graph, y equals absolute value of x, right? If we're looking for x, that absolute value of x is greater than 1, graphically what that means is we're looking for parts of the graph that are above the line y equals 1. So if you just draw, where's y equals 1? It's something like this, right? So the points where you have, absolute value of x greater than 1 are here or over here, right? So on the right, we have the condition x greater than 1. On the left, we have the condition x less than minus 1. So how do we express those inequalities in terms of containment in a set? Well, we would write, you could say x is an element of 1 to infinity, whereas over here, x is an element of minus infinity to minus 1. So for x to be in the solution set to this inequality, we either need it to be in that set or in that set. And when you want to capture that idea, you use a union. So the solution set is minus infinity to minus 1, unioned with 1 to infinity. And this set that I just boxed in is not connected. It's not connected, right? Have you guys talked about union and intersection before? In some class before? Do you guys know what union and intersection is for sets? I see at least one person saying no, so I'll just introduce it. It's not complicated. The union of two sets is when we take two buckets of elements and just put them together and make a bigger set, which has possibly bigger set, which has all of the elements of both of the sets we're unioning. Intersection, on the other hand, we look at two sets and we see what is common to both of them, and that's the intersection. I'll give an example of both. So this is disconnected because if I were to draw this on the number line, right, what would it look like? It goes minus infinity to minus 1, right? And then 1 to infinity. So I can't draw this set without lifting my marker. That makes it it's not a connected set. It's not one of those 10 basic ones. All right, enough about that. So A union B is x such that x is an element of A or x is an element of B. That's the definition. A intersect B is x such that x is an element of A and x is an element of B. This is union and intersection, where I'm supposing that both A and B are sets. Right? A set is a collection of elements. It's not really a definition, but that's what we say. It's kind of a basic idea. Examples. If we say 0, 1, let's say 0, 10, unioned with 8 to 12 included, what would we get? what would the intersection of those be? What would the... I heard... What was the first one?
I was looking at the bottom.
Oh, the bottom one you said was, what was it? 8 to 10. Are those included or excluded? Included, right. And if you're wondering how she knows that, maybe she's thinking about a number line, right? 0 to 10. Now, ordinarily I just erase that with my finger, but there, 0 to 10 versus 8 to 12. Right. So the intersection is where both of those things are, right? So that's like right in here. So that's why I put, oh, the 10's not included, right? So that's, I have that answer there for the intersection. But the union is the whole thing. We put them together, right? So in this case, in interval notation, the union of those two is what? It's, you guys tell me? What is the answer to this one? What's the union of 0, 10, and 8, 12? Yeah, from 0 all the way over to 12 would be what we have there. Now, if you don't understand what I'm saying, then I probably should assign you. It seems like you guys are not quite understanding this. I'm probably going to include a problem or two of this in the homework just to try to refresh. It's really not complicated. You just draw a number line and think about, okay, or versus and you can put it together. All right. So let's see here. Let's move on. So I won't write all this out, but of course we know that real numbers have what? They have a commutative. They have the associative property. You know what the additive inverse of a number is? Like what's the additive inverse of 5? What's that? Negative 5? Right. If that's not what you said, that is what you said. Okay, good. All right, so I would encourage you to reread section 1. Just read through section 1.1. Hopefully nothing there is surprising to you. Let's see here. Absolute value. We should talk about absolute value for a second. What's absolute value? So the absolute value of x is what? It's defined to be x if x is greater than or equal to 0, and minus x if x is less than 0. Do you guys know a formula for absolute value? This is a case-wise defined formula, right? But one of the things that you could also write would be that this is the square root of x squared. See, the square root is defined to be the positive square root, right? So square root of something is positive. And x squared is what? It's also non-negative, right? It's positive if it's positive if x is positive, it's 0 if x is 0. So the point is that formula returns plus or minus x depending on whether x is positive or negative. Here, try it out if you don't believe me. So the absolute value of minus 5 is the square root of minus 5 squared. What's minus 5 squared? 25. What's the square root of 25? 5. So there you go. You can actually write the absolute value in terms of a formula. What's the main purpose of the absolute value for us? What does it do? If I have the number line, right, and I have a point here A, and I have a point here B, and I want to know what's the distance from A to B, how do I get that? How do I get the distance from A to B? I take the absolute value, right, of the difference of A and B. So absolute value b minus a, this gives us distance on the number line. That becomes very important in calculus as we think more about distance there. All right, I think that's pretty much all I have to say about section 1.1. I've spent entirely too long talking about it. My apologies for that. But it looks like there are some pretty good practice problems in this section. I'll try to give you a lean list of those. I try not to give you too long a list. Again, I don't collect the practice problems, but there's a lot of silence here about some of these questions I'm asking. I don't know if that's just because you're bored or if it's because you're genuinely lost. So if you're genuinely lost, you need to work all the practice problems and talk to me about the ones that don't make sense. All right? Not because it's unlikely any of these things are a question on the first test, but it's very likely that this language gets used in questions that you're asked. Right? So if you don't have a firm grounding on what the words mean, it makes it impossible to answer questions that you're asked. All right, so moving on. Where's the rest of my book? So this is good because I can hold this and I can't hold the book, right? But it's also bad because invariably I will lose sections. So anyway, words, exponents and radicals. So let's get to it. I want to review for you. What do we mean? What's a to the n mean for us? It's a times a times a, da-da-da-da, times a. How many times? N-fold times, right? That's what we mean by a to the power n, where n is a positive integer. What are one of the main algebraic properties? If we have a to the m times a to the n, we get a to the what? M plus n. It's an important property of the exponent notation. That's actually still true when m and n are negative. So here I was supposing that n was an element of the natural numbers. Now if n is an element of the integers, and n is less than or equal to 0. So that's just a mathy way of me saying, suppose n is like 0 or -1 or -2 or -3, those sorts of things. Then how do we make sense of a to the n? Well, the way he writes it is, I'll follow the book. Sorry, I guess I should ask this. What would we mean by a to the minus? Suppose n is still a natural number here. What would we mean by a to the minus n? I'll stick with n being positive for the sake of making the discussion more understandable. So then a to the minus n would be negative. What's that mean? What that means is a to the minus 1, right, raised to the n power. In other words, it's 1 over a times 1 over a times 1 over a n-fold times. All right. And the key point here is that a to the m times a to the n is still equal to a to, let me stop using m and n. Let me say a to the s times a to the t is a to the s plus t, and this is true for s and t being an integer. So that rule still makes sense even when s and t are negative, or when s, what would we mean by if s or t is 0, what's that mean? What's a to the 0 by definition? Right. I heard a to the 0 equals 1 there. Very good. So we need that to make all this put together. So what, okay, so, example, if I have 5 to the third times 5 to the minus 2, what do we get? 5 to the third power minus 2, right? 5 to the 3 minus 2, which is what? Yeah, 5 to the 1, which, by the way, is, by definition, 5, right? If you wanted to make this problem harder, how could you do it? Here's what people with a calculator would do, right? They'd say, well, this is 625 divided by 25, right? Because 5 to the minus 2 is 1 over 5 squared, right? So you could also look at this as what's 625 divided by 25? Well, it's equal to 5, right? But it's wiser to not pick up a calculator and to use laws of exponents, right? So that brings me to another point, which is that if we want to take a to the m times a to the minus m, what do we get? We get a, well, I almost, a m minus m, right? Which is 0, right? A to the 0, which is 1, right? So that means that a to the m and a to the minus m, which, by the way, is equal to 1 over a to the m, right? These are what? I asked you what the additive inverse of 5 was. You told me minus 5. That's great. What's the multiplicative inverse of a to the m? It's this, right? This is the multiplicative inverse. So we have two different kinds of inverses we talk about typically, the additive inverse versus the multiplicative inverse. It's important not to confuse those, right? So, all right. What else can we say? If we have two different things, if we have like a, b to the power m, that's a to the m, b to the m, right? That's another property of algebra that we like to use. Let's look at a good example that kind of combines all these things together at once. We'll eventually have a proper wipe for this thing, but at the moment I'm using these. I think they're vinegar. You smell vinegar? I smell vinegar in these things. I don't know. So I'm waiting for my cable internet to start at my rental house in Tuscaloosa. And so we get the kit. We're supposed to self-install, of course, right? Waiting for it to try. And so we plug it into the cable receptacle, and we plug in the cable modem and follow the app. And I can't find anything. I'm like, oh, no. So I think, all right. So I go outside to try to look at where the cable goes to. And what I find is not one cable, not two cable, but like 5 different cables, all going different ways. Most of them cut off at the end. I think every time somebody rents this place, they get a new cable installed. And then when they leave, it gets cut or something. So it's madness. Until I get that, it's hard for me to, I should have kept that. Dang it. It's hard for me to post videos at home, unfortunately. Once I get that, though, I'm going to be able to post videos at night when I feel like it. You're like, you should rest. There's no need to make homework or videos. Just relax, right? Right, okay. Very good, very good. So here, let's look at an actual example. Let's simplify. Let's simplify to, let's see here, I'm going to give good instructions. Positive exponents. right, so suppose you had something like x squared y to the minus 3 divided by x to the 13th, y to the 4th. All right. So I say simplify and leave your answer in terms of positive exponents, right? So that's going to force us to do a certain thing. So what we're going to do is I'm going to be lazy. Here's just kind of I'm going to put everything on one line. So I've got x squared, y to the minus 3. To bring x up to the top, I'll do that. Now, listen, you're like, the way you're doing it's weird. That's true. I'm just doing it a way. It may not be the way you want to do it, and that's okay. So just to have a plan of attack, I'll put everything on one level, combine like terms, and then I should be able to see where to go clearly. Like, what do I have? I've got x to the what? X to the negative 11, and y to the what? Negative 7, right? And so that's not done yet. I said simplify using positive exponents. How can I rewrite this using positive exponents? Yeah, 1 over x to the 11th times y to the 7th. And there you go. That would be how to simplify this expression, right, using laws of exponents. Let's see here. Another example. See if I can find a good one. This one they have in the book. They've got 2a cubed b squared times 3 a b to the 4th power parentheses cubed. Right? Now, just returning to the last problem briefly, a lot of you perhaps, I don't know where you are algebraically, I haven't graded anything that you've turned in, but I know there are some people who could kind of like go straight from here to there and not show steps, right? And that's okay, except that it gives me no way to give you partial credit if you're wrong, right? So it's good to have in-between steps so I can see some indication of where you went wrong, if you went wrong. But that just, I would like to see a step on most things, but if you're uncertain, if you've shown enough work or something on a test, just come and ask me. I'll try to ward off disaster before it happens, Okay, so this one, what do I do? What do I have to do first? Order of operations. I have to take care of that cube first, right? I can't do anything else until I do that. So we'll leave this 2a cubed b squared out front by its lonesome. And then when I take this to the power 3, how does that work? That goes 3 to the 3, a to the 3, b to the 4 to the 3. Right? Because while I didn't write it over here, there is also a rule for products of more things. If I have a, b, c to the, say, m power, it's equal to a to the m, b to the m, c to the m. Right? I am assuming that these things are non-zero in the case that the powers are negative, right? We can't make sense of like 1 over 0. So we have to be careful with like negative exponents that we're not dividing by 0. I haven't said much about that, but that is a concern. Okay, so here, some of these problems, like this one, this problem doesn't even make sense unless we assume that x and y are positive, or at least non-zero, I should say. Okay, so what's next? We've got, what's 2, what's 3 cubed? 3 cubed is what, 3 times 3 times 3? Is that 27? 27 times 2? 54, right? So 54. And I've got, collect my A's together. So I've got this A, And that gives me a to the 3 times a to the 3, which is what? A to the 3 plus 3, which is a to the 6th. All right. I'll put one more step for my b's. So I've got b times b squared. Still that b squared, right? And this is what? B to the what? 4 times 3? 12. So then I have to use laws of exponents again to collapse those to just one single term with b, right? And so the answer is what? So we have 54, a to the 6th, b 14. And there is the answer, assuming that we're looking to simplify to a term with positive exponents. Does that make sense? I hope. Let's see here. I'll look at this, one more example here with exponents. It's example 5 in the version of the textbook I have here. But so the instructions are eliminate negative exponents and simplify each expression. So we have 6 st to the minus 4 divided by 2 s to the minus 2 t squared. All right, so when I see something like this, what I usually do is just leave the positive things where they are, and I move the negative things to. Honestly, how I really do this is I look at all the variables of one type. I've got like s's, right? I've got s to the minus 2, and I ask myself the question, which one's going to win? Yeah, the bottom one, but I need to bring it upstairs, right? Because otherwise then I'd have, if I bring the s downstairs, I have s to the minus 3, but I want my answer in terms of positive, right? So I want to bring the s to the minus 2 upstairs to make the answer have a positive exponent. Does that make sense? I mean, so let's see here. So let's see here. 6, I'll stop talking and just start writing 2t squared. So I'm just leaving those terms alone, right? And then the other terms, that is s squared upstairs, and this is t to the 4th downstairs. So if we move, like this is just a general rule, if I have a to the minus m, then that's equal to 1 over a to the m. And that's still true when it's multiplying other stuff, right? On the other hand, 1 over a to the, say, minus m is equal to a to the m. So if we move a negative power from the denominator to the numerator, it flips to a positive, the same magnitude but positive, and vice versa the other way. These are the two main tools in our toolbox here to convert from negative to positive in these fractions. Okay, so then what would the answer be? And you're like, why did you write 6 over 2? Don't you know 6 over 2 is 3? I do. I like to write sometimes, but it's not. It would have been fine to make that 3 in the last step. So 3s cubed divided by what? T to the 6th. So I should point out there's a big difference. So here's a common confusion. Some people, if they're not thinking, they will confuse t to the squared times t to the 4th, which is t to the 6th, right? Versus t to the squared to the 4th power, which is what? T to the 8th. You see the difference there? We're multiplying like bases with different powers versus taking one base and then exponentiating it further, right? Repeated exponentiation versus exponentiation multiplied. Anyway, there's the answer. Your section 1.2 has now something to say about scientific notation. I don't I'm not covering that, if that's okay with you guys. I'm focusing our attention elsewhere. Radicals. What about radicals? So what do we mean? I think the okay, so definition. The nth root of A equals to B means B to the n equals to A. If n is even, we require A greater than or equal to 0 and B greater than or equal to 0. All right, so, alternative, we could also write that the nth root of A is equal to A to the 1 over n. All right, so what are the properties of nth roots? Like if I have the nth root of A times B, guess what? It's the nth root of A times the nth root of B. And you're probably most familiar with this when the n is gone. When the n is gone by default, what's n? 2, right? The square root is what we usually talk about. But we talk about cube roots sometimes as well, right? So this also works for fractions. So like the nth root of A over B is nth root of A divided by nth root of B. And also there is a, if we take the nth root of A and then take the mth root of A, the mth root of the nth root, the m on the outside is like mommy, the n inside is like nanu nanu, a reference which is more and more lost with each passing generation. Mork and Mindy has not aged well. Let's see here, so m, n, a, like that. Of course, if you write this in the other notation, it's like, of course that has to be true, right? So a to the 1 over n to the 1 over m is what? Right? Which is the same as, because multiplication commutes, and if you believe me, that's the mnth root of A. Now, there is some let's see here. Let's say fine print. N odd. Let me give you an example. The cube root of minus 27 is equal to what? I heard a 3. That will get you half credit. Was that? Yeah, negative 3, right? Because we have to go back to the definition. See, minus 3 to the 3 power is minus 27. right? So the cube root of a negative number will be another negative number is the bottom line. For n even, like the square root of, that's not what I want to say. Let's see here. Oh, okay, so what I want, aw, man. All right, for n even, we can say the following. We can say that, like the nth root of a to the n, it's equal to the absolute value of a. So I think I did that actually a little bit. I think I erased it, but I had up there the square root of minus 5 squared. We got 5. That would be an example of this. Because the positive root, like an even root, by definition in this class is the positive root. Okay? If you guys later go on and take something called complex variables, you'll learn about additional roots. Like in mathematics, we actually have, like generally, if you look at the nth root, there's actually n of them. But we just focus on that one choice where it's a positive root, or a negative root in the case it's negative. Okay, so let me move on. So we start this class when? Ah! Son of a gun. Well, I'm getting there. So we have now reached section 1.3. So I should probably stop there. It's a good place to stop. I'm sorry I am dragging. I will eventually get on pace. So sorry. Oh, and I'll